particle of mass m in the harmonic oscillator potential starts out in the state psi of x and 0 equals some normalization constant times 1 minus 2 square root of m omega over h bar x parentheses squared times the harmonic potential, the harmonic part. The question here, what is the expectation value of the energy? That is, what is the expectation value of h? First of all, let's define the new variables. Let's define the squiggly, because we are talking about the harmonic potential. Is made out of the square root of mass times omega divided by h bar, square root of that times x. Also, let's define alpha as the fourth root of mass times omega divided by pi h bar. With this in mind, let's rewrite our wave function in terms of squiggly and alpha. So we have psi of x and 0 is made out of a times 1 minus 2 squiggly square times e to the minus squiggly square over 2. Okay, so let's expand this parentheses. So our wave function now is a times 1 minus 4 squiggly plus 4 squiggly square times e to the minus squiggly square over 2. Alright, so from here we can rewrite this wave function in terms of the three initial states. So we have the ground state psi of x and 0. This is in terms of alpha and squiggly, it's made out of alpha times e to the minus squiggly square over 2. We have the first exciting state, which is the square root of 2 times alpha times squiggly times e to the minus squiggly square divided by 2. We have the second excited state, which is equal to alpha divided by square root of 2 times 2 times squiggly square minus 1 times the exponential part square over 2. The reason we are doing this is because we want to find this normalization constant a, because we cannot find the expectation value of the energy without normalizing the wave function first. So now if we want to put this wave function in terms of these three, we get psi of x and 0 equal to c naught times psi naught plus c1 times psi 1 plus c2 times psi 2. Furthermore, we have psi of x and 0 equals alpha times c naught plus square root of 2 times squiggly times c1 plus square root of 2 squiggly square times c2 minus 1 divided by square root of 2 c2, and of course this times the exponential term e to the minus squiggly square over 2. Alright, so now if we combine like powers, we get the first one, we get alpha times square root of 2 times c2. This is equal to 4a therefore we have C2 equals 2 times square root of 2 times A divided by alpha. And here we have alpha times square root of 2 times C1, and this is equal to minus 4A. Solving for C1, we get C1 equals to minus 2 square root of 2 A divided by alpha. And finally we have alpha times C naught minus C2 times divided by square root of 2 equals A. And solving for C naught, we get C naught to be equal to 3A divided by alpha. Alright, so now if we normalize this wave function, we get 1 equals to the first coefficient module square plus the second coefficient C1 module square plus C2 module square, which gives us the first one. It's 4 times 2, so that's 8, plus the second one is also 8, and the third one we have 3 squared, which is 9, and of course all of this is times A divided by alpha square. This is equals to 1. Solving for A in terms of alpha, we get A to be equal alpha divided by 5. Alright, so now since we have A, we can find C naught divided by, which is equal to 3 over 5, right? And we have C1 is equal to minus 2 square root of 2 divided by 5. We have C2, which is equal to 2 square root of 2 divided by 5. Finally, now we can find the expectation value of the energy, which is equal to the sum over n of C sub n module square times n plus 1/2 times h bar omega, which gives us the first one. So we have 9 over 25, n equals 0, so times 1/2 h bar omega. The second one we have 4 times 2, so 8 over 5 times 8 over 25, because we have square, right? 8 over 25 times 3/5 h bar omega. And finally the last one is 8 over 25 times 5/2 h bar omega. Simplifying this a little bit further, we get the expectation value of the energy equals 73 over 50 times h bar omega. And there you have it. Let's look at another example of the simple harmonic oscillator with the equation for the potential energy V of x equals 1/2 m omega square x square. Now we need to show that this psi function satisfies the time-dependent Schrödinger equation for the harmonic oscillator. B, we need to find the probability density, and then finally C, we need to find the expectation value of x, the expectation value of p, and we need to check that the Ehrenfest theorem is satisfied. So let's get started. First of all, we need to check that this wave function satisfies the time-dependent Schrödinger equation. Of course, let's take one time derivative of the wave function. This gives us minus m omega divided by 2h bar. So partial derivative, we know that partial derivatives are easier than normal derivatives. Divide by 2 times minus 2 omega e to the minus 2 omega t plus h bar divided by m minus 2 x times omega times e to the minus omega t times psi. So let's multiply both sides by h bar and simplify a little bit. If we do this, we get minus 1/2 ma square times omega square times e to the minus 2 omega t plus 1/2 h bar omega, this should look familiar, plus ma times x times omega square times e to the minus omega t, of course, times psi. So now let's take one x derivative of psi. So the partial derivative of psi with respect to x is, you know, you do the derivative and you do some simplifications, you get minus m omega divided by h bar times x minus a e to the minus omega t, of course, times psi. So now let's take another derivative, so of x. So now the second partial derivative of psi with respect to x is equal to minus m omega divided by h bar times psi minus m omega divided by h bar times x minus a times e to the minus omega t, and this is the partial derivative with respect to x. Let's simplify this a little bit. So second partial derivative with respect to x equals to minus m omega divided by h bar plus m omega divided by h bar parentheses square times x minus a e to the minus omega t, and this is square times psi. So now let's look at the harmonic oscillator equation. So we have minus h bar squared divided by 2m times the second derivative of psi with respect to x plus the potential energy, which is 1/2 m omega square x squared times psi. So if we plug the second derivative here, we get this equals to, after some simplifications, we get 1/2 h bar omega minus 1/2 m omega square times x square minus 2a x e to the minus omega t plus a square e to the minus times 2 times omega times t. And we also have the potential energy function, which is 1/2 m omega square x square and of course all of this is multiplied by psi. Alright, so let's simplify this a little bit further so we can see what it looks like. So this is gonna equal to 1/2 h bar omega plus mass times a times x times omega square times e to the minus I omega t minus 1/2 m omega square a square times e to the minus I 2 omega t times psi. Of course all of this times psi. And indeed this is equal to I h bar, the partial derivative of psi with respect to time. There we go. So this is number 1. So part B, we need to find the probability density. So that's psi star psi. So it's going to be a little bit tricky, just bear with me. So now we have, you know, the fourth root of this term. We have it twice because we have psi star psi. So the fourth root becomes the square root, and then we have e to the, so this is e to the minus m omega divided by 2 h bar times, we have x square plus a square divided by 2 times 1 plus e to the 2 I omega t. Notice there's no negative because this is psi star. This is minus I h bar t divided by m minus 2 a x e to the I omega t. So now we have to add plus, this is the psi term now, we have x squared plus a squared divided by 2 times 1 plus e to the minus 2 I omega t, right? So close that. Now plus, it's negative here because it's conjugate, right? Now it's plus I h bar t divided by m minus 2 a x e to the minus I omega t. Close parentheses, close brackets. So now let's simplify this a little bit further to make it more meaningful. So after a lot of algebra, we get the square root of m omega divided by pi h bar times e to the minus m omega divided by 2 h bar times, this is to the power, okay, so this is times, we have 2 of these x's, and we have plus a square plus a square cosine of 2 omega t. Just bear with me, if you don't know where this cosine came from, that's fine, minus 4a x times cosine of omega t. Notice that a square, but what we know that here, let's put it in the box here. We know that a square times 1 plus cosine of omega t, we know this is equal to 2 a square cosine square omega t. Right, so let's use that. So this is gonna give us square root of m omega divided by pi h bar times e to the minus m omega divided by 2 h bar to the power of x squared minus 2ax cosine omega t plus a squared cosine square omega t. Okay, so now let's simplify this one more step. So this is psi star psi equals to the square root of m omega divided by pi h bar times e to the minus m omega divided by h bar times x minus a cosine omega t square. There you have it. This is the probability density. This is the probability density for this wave function. So the wave packet is a Gaussian at a fixed shape whose center oscillates back and forth. Okay, so the center of this Gaussian packet oscillates back and forth with amplitude a and frequency omega. So this is the amplitude, this is the frequency. So now let's say find the expectation value of x. So you sandwich x between psi star psi, right? So what we have the integral of x times psi star psi. It's better to put it in between, because in this case it's not, because x doesn't really affect what comes after it. But when you have other operators than x, for example, if you have the momentum operator, you need to put it in between. So this gives us the integral of y plus a cosine omega t times, parentheses here, times psi star psi dy. I'm sorry, I made change of variables here, so here you let y, we defined it as x minus a cosine omega t. So this is y, so just solve for x, find what x, and take a x derivative to substitute for this. So this is going to make things a lot easier on us. So now what we have 0 here plus a cosine of omega t times the integral of psi star psi dy, which is 1. So this gives us a cosine of omega t. So now the expectation value of p, this is the same as m times the time derivative of the expectation value of x. Make things a lot easier. So just take time derivative of this, and that gives us minus m times a times omega times the sine of omega t. So now let's see if let's take a time derivative of this expectation value of p. So this gives us minus m a omega square cosine of omega t and we know that the potential function, the potential energy here is 1/2, it's the harmonic oscillator potential energy, m omega square x square. Let's take one x derivative of that, so dv dx is equal to m omega square times x, and finally if we take the expectation value of the negative of this, this is the same as minus m omega square times the expectation value of x, right, which is equal to minus m omega square times a times cosine of omega t, which is the same as the time derivative of the expectation value of the momentum. So therefore the Ehrenfest theorem is satisfied.